Heyo! All right, so we've looked at natural log and 1 over x. So now we're going to look at e to the x. Hooray! So e to the x and natural log are inverses of each other. So in our picture, this little guy here, that's the natural log. And this one right here, that is e to the x. And something we're going to notice is that e to the x and natural log, the x's and y's are swapped. This is going to come into play in a later section, so that's a really important thing for us to understand, is that with inverses, x's and y's trade places. So, so in order to handle something like this, we can solve some equations and, okay, fine, I'll go into it. So, if we have y is equal to natural log of x, the way that we would find its inverse is by, instead of writing y, we'll write x, and instead of writing x, we'll write y. And so now to get y by itself, I'm going to take e to both sides, which cancels out my logarithm and leaves me with e to the x is equal to y. So the thing about inverses is they need to work no matter which one you start with. So if I were to start with y is equal to e to the x, and I do replacement x is equal to e to the y, then I can take the natural log of both sides. You may remember that natural log of e to anything, the ln and the e kill each other, and you're just left with a y. So these are in fact inverses of one another. Another thing that you can see when you plug an inverse into its function, so if I were to take y equals natural log of x, and instead of writing x, if I were to write its inverse, e to the x, then using algebra, I can bring the x out front and get x natural log of e, and natural log of e is 1, and we get x, which is what you're supposed to get as a way of checking inverses. And similarly, if I started with y is equal to e to the x, and I said y is equal to e to the, and I plug in its inverse, natural log of x, e to the natural log cancel each other out, and we're left with x. So two different ways to kind of show that these are inverses of one another. So Mr. Keenfield, I didn't get any of that. Don't worry about it, who cares? So, excuse me, did I say that? So we can use this fact to solve stuff like this. So if I have a number is equal to e, I could take the natural log of both sides. I wrote that wrong. Hey, professionalism. So I could take the natural log of both sides. And again, using some algebra, we have the natural log of 7 is equal to x plus 1 times the natural log of e, which this dies, and because it's just 1, natural log of 7, and then take away 1 from both sides, and we're done. So natural log of 7 minus 1. I don't have my calculator on me, but I'm going to assume that is between, probably between 1 and 3. So I don't know what 2.7 is squared off the top of my head, but, and then over here, if I was going to try to solve this one, I see it's natural log of x plus 2 squared. First thing I would do is bring the 2 out front. 2 natural log x plus 2 is equal to 10, and then divide both sides by 2. And get natural log of x plus 2 is equal to 5. And so over here how we ln both sides, we can e both sides here. Whatever this base is, and since it's an e base, we'll do that. And the e and the ln cancel, we get x plus 2 is equal to e to the 5th, which is some number, and then we can subtract 2 from both sides to get that. Now, on a multiple choice exam, natural log of 7 minus 1 and e to the 5th minus 2, that's most likely the way that you would see it. They don't really care if you can just plug all 4 answers into the calculator or all 5 answers into the calculator. So that's important to note. None of this was calculus. Here's some more not calculus. All right, so domain. Remember, domain is how far left and right does it go? Well, domain e to the x goes all the way from negative infinity to infinity. And range, it goes all the way up to infinity, but the lowest it gets, it actually has a horizontal asymptote at 0. So, and it never actually equals 0. It is certainly continuous. There are no breaks. There are no issues anywhere on the real number line. And its derivative, e to the x, has a very strange situation where its derivative is itself. Why? Oop, I crossed that out. All right, didn't want to take time to talk about that. And then its second derivative, well, if its first derivative is itself, then its second derivative is also itself. Hooray. So if anybody is really annoyed that I skipped talking about the y, let me know. I'll toss another video up on it, or maybe we'll talk about it in class when we do it. All right. E to the x is never equal to a 0. All right. The limit is e to the x approaches infinity. So that's as it goes this way, it's infinity. It's going up and up and up and up and up. Remember, that's a special form of does not exist. And as it approaches negative infinity, it's not going down, 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 down to negative infinity. It's going down, 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 down to this flat horizontal asymptote at 0. All right. So, do you remember your exponent operations? When we multiply two different exponents that have the same base, we just add them. Remember, this is e times together a times, and this is e times together b times. So if I have a times and b times, then that's going to be a times and b times together. That's why it's a plus b times. Similarly, this is a times and b times. So we wind up crossing out however many overlaps there are, and we're only left with however much more a is than b. And if b winds up being more, then we wind up having some e's left over down here, and that's why we say that this is e to the a minus b. This one, this would be e to the a times, and do that a total of b times. So it'd be e to the a, or like, it'd be like e a times, over and over and over and over and over again until you get to b. Because of that, we multiply these two, and that's how many it is. If you didn't follow all that, go back to Algebra 2, Algebra 1, whenever you learn this for the first time. Or honestly, again, I can spend more time on this in the future if you need it. Okay, now we'll do calculus. So remember, the derivative of e to the x is e to the x. It is the best derivative ever. It's your best friend. So the derivative of e to the u, let's say it's something else, e to something else. It's going to be e to the u times du, times whatever, or sometimes in our class we'll say times u prime, times whatever the derivative of that is. So here, e to the 3x, the derivative is going to be e to the 3x times the derivative of its exponent, which is just 3. I don't like writing it like that. I personally prefer to write 3e to the 3x. And this is, a lot of the world prefers to write it this way. So, like in this one, our derivative of the exponent is 10x plus, woof. We have to do a chain rule on that, don't we? So the derivative of the inside is 2. I'm going to do that first. And then it's going to be secant tangent, right? Secant 2x, tangent 2x. So that's the derivative of meh. And then we just do times 5x squared plus secant 2x. So I did my derivative of the inside times, the derivative of my exponent times whatever we started with. So it's annoying, I know, but just make sure that your chains pop out and follow the right orders. So on our next one, I could, if instead of kind of writing all the inside stuff first, if you want to just write e to the negative 4 over x first, that's great. And then the derivative of this, remember 4 over x, we're not taking the antiderivative. This doesn't bring natural log in. This is just saying take the derivative of negative 4x to the negative 1. So we multiply by negative 1, and we get positive 4, and then we subtract 1 from our power. So you could say 4x to the negative 2, e to the negative 4 over x. If you really want to rewrite it, you could bring that x to the negative 2 down to the denominator. And you could write it like that. So, all right, we'll keep going. So these are more just using derivative rules with e's in them. So this would be a product rule question, right? So we know the derivative of that on its own is 2x. The derivative of this on its own is e to the 2x times the 2 from that, because the derivative of 2x is 2. So I could write 2x e to the 2x plus x squared times 2 e to the 2x, or 2x e to the 2x plus 2x squared e to the 2x. Let's talk about factoring. On a multiple choice exam, they probably wouldn't leave it like this. They would probably factor out the 2, the x, and the e to the 2x from both of them. If we do that, in our first one, we're left with 1. In our second term, the 2 goes away, the e to the 2x goes away, and one of our x's goes away. So they might write like that, or they might even rearrange the inside of that to x plus 1. So, yeah. All right, in our next one, we know the derivative of the top is cosine, the derivative of the bottom is e to the square root of x. Oh, and then we gotta take the square root of x's derivative, which is 1 over 2 root x. So, here we go. It's a big division bar, which means quotient rule. So I'll take the derivative of the top, leave the bottom alone, minus derivative of the bottom. Derivative of the bottom, which is 1 over 2 root x, e to the root x. Leave the top alone. Oh, just such a relaxing, easy to look at problem. Cool. No problem whatsoever. All right. Well, we're not allowed to end with fractions and fractions. So I need to multiply the top and bottom by 2 root x. Woof. All right. So that leaves us with 2 root x cosine x e to the root x. Mr. Canva, that's a big mess. I know. Plus e to the root x sine x. All over 2 root x. Now, don't say this is e to the x. Remember, these get multiplied. So this is really e to the 2 root x. I might have glossed over too much up here. Multiplying by this denominator to both of these, the 2 root x and the 2 root x are going to cancel out in this one, but not in the left-hand one. So that's why the left-hand one gets it and the right-hand one doesn't. Okay. In our next example, you may want to distribute the 2 inside here and get e to the 8x first. But let's say you didn't think about doing that. So we can bring the 2 out front because we're doing chain rule. It's now a 1, and that's e to the 4x times the derivative of this, which is that, times the derivative of its inside. So you could rewrite all of this as 8 e to the 4x times e to the 4x, which is silly. Don't write e to the 4x times e to the 4x. Those have the same base, so we can add their exponents. Now, wasn't that nice? So, again, lots of chains and it works. You could also, like I said, multiply these 2 exponents and get e to the 8x and take that derivative instead, which would just be e to the 8x times the derivative of the inside. So I don't know why you would prefer to write like only 3 symbols when you can write all this mess and get the same answer. Just kidding. So sometimes doing some cleaning up before we take a derivative, it saves us so much time. And honestly, this is a lot messier to think through as well. All right. So now we have the derivative of a natural log of an e to... So instead of dealing with all of that, this is the natural log of something to an exponent. So we could rewrite this as 7x squared plus 3x times the natural log of e. And we're taking that derivative. Well, what do you know? Natural log of e dies, and we're left with the derivative of 7x squared plus 3x, which is just 14x plus 3. Mr. Canfield, I don't believe you. All right, let's check it out. If you don't believe me that that's the answer, let's see. Take the derivative of the natural log. You flip the inside. That's 1 over e to the 7x squared plus 3x times the derivative of the inside. The derivative of the inside is the inside because it's an e thing. E to the 7x squared plus 3x. Then times the derivative of its inside, which is 14x plus 3. Well, what do you know? 1 over something times the same thing. Guys, these cancel, and we're left with that. So I win this time, at least. So, go me, hooray, woo! The next question says, find the relative extrema. Ooh. Remember, relative extrema, we want f prime of x to either equal 0 or undefined. So, at least that's the start. We call those our critical numbers. I have 5 minutes. Let's see if I do it. So, let's find our f prime first. So f prime of x is equal to, we have to do product rule. That's 1 e to the negative x plus x times the derivative of this is going to be e to the negative x, and then times the derivative, so negative 1. So I'm going to change this to a minus. So 0 is equal to e to the negative x minus x e to the negative x. So I'm going to factor out an e to the negative x and get 1 minus x. So x is equal to 1 because this is never equal to 0. And this one, remember, this is 1 over e to the x. So I could actually say, oh, is there ever a point that this is undefined? Is there ever a point this is 1 over 0? But e to the x, as we stated earlier today, is never equal to 0. So no. Excuse me, this has no value. So 1 is a potential relative extrema. Remember, to test our relative extrema, we take our x value and we plug that x value into f prime. So we use 1, and then we use numbers on either side of our critical number. So I'm going to use 0 and 2. So if I plug 0 into our f prime, so e to the negative 0, that's e to the 0, that turns into 1, and I subtract 0, so I'm left with a positive number there. Don't believe me, do it yourself. This one, we're going to 0, and then this one, if I wind up doing this, I wind up getting a negative number out when I do it, and so because of that, our slope goes from positive to flat to negative, and so I know that 0, I don't know, is our